Okay, so I hope you get back. Our main speaker today, Olivier Gossner, professor of economics at École Polytechnique, professor of mathematics at London School of Economics. He's currently a director of research at CNRS, a fellow of the Game Theory Society. He works on many topics as value of information, repeated games, finitely or infinitely repeated, incomplete or complete information, perfect or imperfect monitoring. And today he's going to talk to us about robustness to incomplete information and algebraic characterization. Olivier, the stage is yours.
Okay, thank you so much, Galit. Thank you to the organizers for having us and for the audience for coming. So the title changed a little bit. You see probably a new title now on your screen. New title doesn't emphasize so much the question of robustness. I'll be talking about robustness. And this new title is Rationalizable Distributions in Games with Incomplete Information. And there is still an algebraic characterization, but we'll talk about this. Okay, so what is the main question we address? So we look at a game with incomplete information. What is a game with incomplete information? It's given by states of nature that describe what can impact preferences or payoffs of the agents, choices, action sets for the agents, and their preferences or their payoffs if you want. And we look at such a game and we say, we don't know what is the information that the agents have. And we ask, what can we say about the outcomes in the game when we don't know what the information is? So this is a relevant question for different reasons. One is that from the, say, positive point of view, you may imagine hypothetical situations where you know the strategic interaction between a group of agents, you don't know what information they have, and you would still like to make predictions about what's going to happen in their strategic interaction when they have this information and they have to make choices which are known. The second point where it is relevant is, we call it information design here. It would be, how do we want to distribute information to the agents? If we could design the information the agents receive, how would we design this information in order to achieve certain outcomes? So just similar to mechanism design, except that here we don't design the game played, but we design the information to the agents. And a third question, which is very related, is the question of robustness of equilibria. I call it here on the slide adversarial approach. Basically, what I mean by this is that we imagine that we like to implement a certain outcome, but somebody who is against the outcome, I mean, it's hypothetical, would want to design the information of the players in such a way to maximize the chances to destabilize our outcome. Okay, so the question is, can you destabilize an outcome? And if you can destabilize it, it's not robust. Okay, so that's a quick simplification of what robustness means. So of course, the question is well addressed in, depending on what we care about in terms of outcomes in a game. So there is a solution concept, which is take a game, like I said, you fix states of nature, preferences, actions, and then you make information arbitrary to the agents, and you look at the Nash outcomes, the Nash equilibria of the game of incomplete information, where players get the information first, then play the strategic information in the game with incomplete information. And the corresponding notion is correlated equilibrium distribution with complete or with incomplete information. That's how we obtain these correlated equilibrium distributions. Okay, here we are going to look at a different solution concept, which is not Nash and which is interim correlated rationalizability. So there are different reasons why we may be interested in looking at something which is not Nash. One is, okay, well, why not? This is an interesting solution concept by itself. In terms of epistemic foundations, there are differences between Nash, or let's say correlated equilibrium distributions, and interim correlated rationalizability. So if I'm not mistaken here, when you look at correlated equilibrium, you look at common knowledge of Bayesian rationality. This is according to Ullmann. And if you look at interim correlated rationalizability, you look at common certainty of rationality. Okay, so it's less demanding in terms, say, of rationality. The other reason to look at interim correlated rationalizability is that it's a set solution concept. So when you fix an information structure, you will have a set solution concept, and this set solution concept is more fit to be applied to the question of robustness of equilibria than correlated equilibrium distributions, where you catch too many things basically, and you can't know through correlated equilibria if you're going to have something robust or not. But I want to talk about this, just only very quickly in passing, and perhaps at the end of the talk we'll come back to the question of equilibrium robustness. Okay, are there questions maybe about this bird-eye view of what we're trying to do? Okay, so well, the slide on literature. So this is related to different strands of literature, I would say. First one is solution concepts. So looking at correlated equilibrium with complete information. This is the paper of Aumann. With incomplete information, there is the paper by Francois Forge. Then there is something also interesting, which is kind of a little bit in between, which is base correlated equilibrium. I say in between because Bergerman and Morris, in their solution concept, they say, okay, you have a game and you have certain information that the players have, okay? And now to this, you may add extra information, okay? So that's base correlated equilibrium. And this concept will depend on a strategic interaction and on a basic information structure, which you already have, to which you may add some information. We will be relying extensively on the concept of interim correlated rationalizability, as I mentioned, by Deckel, Fudenberg, and Morris, 2007. Now, the second strand of literature, which is really a motivation for what we are doing today, but then we realize like we cannot do everything, give you what I want to give you today really nicely, and robustness. So this motivation is robustness. One of the pillars, I would say, is the 87 paper by Rubinstein on the email game. There are different versions, so to say, of robustness, going through global games and formalizations of Keiji and Morris, or Yama Takahashi, on characterizations also of what can be robust. The big question here, or the big difficulty in in studying of robustness, is that it's very hard to go beyond games with 2 strategies per player, and so that's really we hope that we can push for much bigger applications or much more general applications of robustness to be able to use the concept of robustness in a much more general concept of games, but that's not really the topic of today, as I said. Okay, so one way to view what we do today is the question of information design. So there are different things, different parts of this literature. One is without common priors. So what do we mean by without common priors? Vanchen and Yildiz, what they do is they say, okay, can I design a type for one player? Okay, I don't care about the whole information structure, with common prior that this could come from, because I don't care about common prior. And how can I design types of players in order to destabilize certain actions, or in order to select certain actions of a player in a game? Okay, so we will insist on having common priors because most of game theory is with common priors. Without common priors is also certainly very interesting for the sake of it. One-sided incomplete information. So what do we mean? We mean here that one player is informed of a state of nature, the other player is not informed, and we ask what happens in terms of when we give some information to the non-informed player, and the seminal work is Oman Mashler. A lot of applications follow the work of Kaminicka and Gensko on similar model. I want to say here, finally, that robustness is already, the study of robustness is already leading to the question of information design, because there is a paper by Morris Oyama Takahashi that takes the question of robustness and opens it or frames it, let's say, in a question of information design. Okay, So that's for literature. So now what do? We want to define and characterize what we call rationalizable distributions, okay? And you want to think of rationalizable distributions in a way that parallels very much correlated equilibrium distributions. So basically the idea of rationalizable distributions is you're going to have the same definition as for correlated equilibrium distribution, except that you want to replace Nash by interim correlated rationalizability. So you take a game, you fix the strategic form played by the players, and then you vary the information that the players receive. For each such information structure, you apply interim correlated rationalizability to the game of incomplete information where players receive the information and play the strategic interaction. For each of those, you will obtain a distribution of outcomes, and you will call this distribution of outcome a rationalizable distribution. And you're interested in the set of rationalizable distributions that can be generated in such a way. You're also interested in representations. Just like with correlated equilibrium distributions, you want to know how you can implement those distributions, not just which ones you could implement. So that's what we'll do. We'll obtain a characterization of such rationalizable distributions, more precisely of a subset of them of interest. This will go in steps. The first step, just very much in the spirit of the revelation principle, is to use a canonical state space. And here I'm going to rely on what Rafael has just presented by saying that this strategic state space is a good canonical state space for our purpose. Then once we have this canonical state space, we want to have a representation that has a recursive form. And this recursive form will really go through the automaton. So it might be a slightly different automaton from the one presented by Rafael because it's tailored to a slightly different purpose, but the idea is the same. You want to capture this idea of recursiveness by a finite generation of your strategic state space. Okay, and once you have the automaton, you want to reduce the problem of finding the rationalizable distributions by a problem that has only a finite number of dimensions on this automaton, and this will lead us to an algebraic characterization, meaning everything you want to do is polynomial. Okay, so let me come back to quickly to the notion of interim correlated rationalizability. We start with a game with incomplete information. So now to fix the ideas, we have a set of states of nature, which is denoted by K. So we have a set of actions AI for each player I, and we have von Neumann-Morgenstern preferences for each player UI, going from the states of nature times A. So A is the profiles of AIs, those are the action profiles, and to the real numbers. Okay. And we will need to have as a notation BI, which is a set of non-empty subsets of AI, so P of AI. So B is a set of subsets of AI. Now let's look at the concept of interim correlated rationalizability. So this concept hinges on a concept of best response. So we think that player I has a certain belief over the state of nature and what other players may have as, let's say, available actions. Okay, so B minus I is a profile of subsets that could be from which the other players could be choosing their actions. Okay, so a conjecture is given by, for every K and B minus I, every subset of the players, we think that the distribution according to which the other players are going to play is a certain sigma of K and B minus I, which of course has support this B minus I, this profile of action subset for the other players. So we have a conjecture of player I, more precisely has a conjecture like this for every state K and for every profile of action subsets of the other players. So if player I has such conjecture on how the other players are playing, and also has a certain belief Pi over the K and B minus I. This means that this player has a belief jointly on K on the actions chosen by the other players. And therefore, we can look at the best responses of player I. And we look at the best responses to PI as the set of all possible best responses when we take all the possible different conjectures that player I has on how other players may be choosing their actions. Okay, well, this is the main step in defining interim correlated rationalizability. Now let's look at the common priors information structure. This is given by a probability distribution P over K state of nature and T. So T is a productized space. Each player I is in form of the component Ti. And how do we compute interim correlated rationalizability? Well, we start by saying at level 0, for each type of each player I, this player has a set of actions, which is a whole set AI. And from this moment, we're going to reduce the set of actions from which player I can choose by selecting only best responses to smaller and smaller sets. So we assume that by induction, ICR has been defined up to level M. And we say that ICR at the level M+1, when the type of player I is Ti, is obtained as a set of best responses to what's inside here, which is a conditional probability given player I's type, which is Ti. There is a certain belief on the other player's types T minus I on and on K. And because ICR has been already defined inductively or recursively up to level M, there is a certain belief on what are the sets ICR at level M that can be chosen by the other players. And therefore, we look at the best response over this belief. So inductively, we obtain ICR 0, ICR 1, and so on and so forth. And we define the notion of ICR as the intersection of all these sets. So this is a decreasing sequence. It's easy to see that this ICR decreases, and if conjectures are more and more pinned down, because the sets from which the other players can choose become smaller and smaller, then the set of best responses also becomes smaller and smaller. Therefore, it can only decrease. Okay, so these are non-increasing sequences, and the concept of interim correlated rationalizability looks at what happens when we take the whole intersection of the whole sequence. Okay, so far it's just a standard definition. Now let me pose the question that we have in mind in these terms. So we are interested, so if you have any such P, so remember P is a common prior. If you have any common prior, there is a distribution of K, there is a distribution of types for all the players. So therefore there is a distribution of K and ICR, which is this limit concept, when K and T are taken randomly according to P. And we say that the distribution which is obtained here is what we call a rationalizable distribution. Sorry, I will do like this. Okay, it's a rationalizable distribution. Okay, now what is a rationalizable distribution in terms of objects? So it's a distribution over K and ICR of T. So what is ICR of T? Remember that every level, given any Ti, you have a set of action profiles that is possibly selected by player I. So ICR of T is an element of B. Okay, B is the profile of action sets for all the players. So this set of rationalizable distribution is a subset of the set of probability distributions over K times B. Okay, so it's not exploding. This is something that can be characterized in finite dimension if you want. Okay, there is finite number of parameters to characterize rationalizable distributions. Okay, now we are not going to be interested in all of them. Well, we are interested in all of them, but our result will apply to a subclass of them, which is a subclass that basically gives you more information about what the players are going to be selecting than any other one. So let me tell you one example. One example would be where the whole set of actions for all the players is rationalizable. Okay, so, well, you don't predict anything, anything can be chosen. The other distribution, rationalizable for this game, would be that a certain action profile is selected with probability 1. Okay, so the second one gives you more information than the first. And we're interested in the ones that give you more information than any other in the family of rationalizable distributions. And this is why we introduce this definition of one distribution more specified than another one. So if you take two distributions, we say that mu is more specified than mu prime if for every k and b, the probability that mu puts on subsets of B, okay? So your at least as determined as B is at least the probability that mu prime puts on the subsets of B, okay? So this is like first order stochastic dominance if you want, but applied to distributions, okay? So that's the notion of more or most specified. I mean, the most specified rationalizable distributions are the ones such that there is no other rationalizable distribution which is more specified than it in a strict sense. Okay? Any questions? Okay, thank you. So the main result is this. The main result is a full characterization of the set of most specified rationalizable distributions. Okay, and we will also tell you, well, if you know one, now you can compute one using, you know, all the tools that we are, going to show. Assume that you compute one and you say, well, that's the one I would like to implement. We will also tell you how to construct an information structure that will implement this most specified rationalizable distribution. Okay, so this goes in steps. Okay, I already hinted at this. The first step is going on a canonical type space. That's going actually to be the strategic type space that was presented by Rafael earlier. The second step is, you see this definition of ICR, it's really all recursive, right? I mean, it doesn't look very complicated. You know, you have ICR m depends on ICR m minus 1 in the same way that ICR m plus 10 depends on ICR m plus 9, okay? So you see that there is a strong recursive structure in the definition of ICR, and we really want to be able to use that. But the main question is, what is the right instrument to capture this, okay? And we tried different things before we could pin down well, at least one right way to do that, okay? Which is through what we call the strategic automaton. And transitions of the automaton, or path, if you want, on the automaton, will represent precisely the path which you can obtain in ICR. Okay, so you start with everybody choosing everything, and then you will start moving on this automaton, and the path will give you the possibilities for ICR. Okay, but they give you the possibilities, they don't give you necessarily all the distributions. We're really interested in the distributions of ICR, and we will see that we can restrict attention to Markov chains on this automaton, okay, which is a strong result because, you know, not everything, of course, which is a process on the automaton will be a Markov chain. And once we restrict to Markov chains, we are happy in the sense that the strategic automaton has only a finite number of states. Markov chains have therefore only a finite number of parameters, which is how you exit each of the possible states. And therefore we reduce the problem, let's say, to a finite number of parameters, but we'll see that's not yet completely the solution, okay? Because the finite number of parameters we'll have on Markov chains will have potentially an infinite number of constraints, and we want to reduce the problem further to a finite number of constraints, and we will show a way to reduce to a finite number of constraints, okay? So once we've done this, it means that we have a representation of the problem through a finite number of parameters, but as I said before, the problem is finitely dimensional. So it's not, you know, nothing extraordinary to have only a finite number of parameters. But we also have a finite number of constraints, okay? And all of these constraints will be algebraic, so therefore the set of rationalizable distributions is an algebraic set. Questions? Okay. So, quick reminder of definition of strategic type spaces. So here I don't I don't care about the axiomatization of this type space. What I care about is, you know, what does it look like? Okay, so we fix again with incomplete information is going to be fixed for the rest of the talk. okay? And we look at SI, which is the set of potential ICR hierarchies for player I, okay? So these are, you take for any common prior, you take any type of player I, and then you look at the sequence ICR0 of this type, ICR1, ICR2, ICR3. That's going to be one particular sequence, and that's going to be one element of SI. Okay. Now, of course, if you take another type, if you take another common prior, you're going to have another sequence. Okay, fine. Then you have another sequence. You look at the set of all the possible sequences that can be generated when you take any such common prior and any type on the support of the common prior for player I. Okay, and we take as the product of all the SIs. So the strategic type space is the type space, or K times S. Okay, it's K times S. So now you see that if you take any common prior, you will compute ICR from the common prior. So you will have a distribution on K times sequences for each of the players of ICR. Okay, therefore, you have a probability distribution over the strategic type space. Okay, well, just by application of ICR moving from types to S by ICR. Now, there is another way to look at the strategic type space, and I think that here there is a strong analogy also with Mertens and Zamir, which is that if you take a distribution over the strategic type space, you have a distribution of K times a product space of, well, what can be considered as types for each of the players. So that gives you an information structure. There is K, which is drawn according to your probability distribution, and you also have a profile of types SI, and each player I is in form of SI. So that gives you also an information structure, okay? So we'll see what we want to do here. The question is, well, can we reduce the problem basically to information structures that are information structures on the strategic type space? And the other question is, what are the distributions on the strategic type space that are induced by common priors? Okay, so if you take all possible common priors, you map each of them on the strategic type space, and then you obtain a set of distributions on the strategic type space. You see, the advantage of doing this is that you reduce the problem from all the possible priors on everything to only priors on the strategic type space. Okay, one thing that I want to say here is that, of course, if you know the distribution on the strategic type space, you know the sequence of ICR for each player I, therefore you know the limit point. So the all the rationalizable distributions are characterized once you know how to characterize all the distributions on the strategic type space. So let me now make clear what we do, okay, on this. So my last comment was exactly this. It's enough to characterize the images of common priors on the strategic type space. Okay, so what are they? What are these images? So what we want to characterize is the set of images of common prior distributions on the strategic type space, okay, because they give us all the information we want. And so we have this result here written as a lemma that says we have a characterization of this set. It is such a distribution comes from a common prior, okay, if and only if it comes from itself as a common prior. So that's quite pleasant, because if you know it comes from a common prior, you don't have to look for an arbitrary common prior somewhere else. It is the image of itself. And the third thing is that it has to satisfy the family of obedience constraints. So let me go through the family of obedience constraints again. So what do we say? We say, well, first condition here is that if you have a distribution that's coming from a common prior, if you have a distribution of ICR, in any case, the first level is that the first level of ICR is everybody selects everything. So it has to be the case that your distribution puts probability on the zeroth level type of everyone being the full set of actions. Okay. Now, we say it has to be the image of itself used as a common prior. So we say, basically, if you know your own type, if you're told a certain sequence of ICR, and based on that, you compute what is your real sequence of ICR based on your beliefs, you should obtain the same sequence of ICR, okay? And this means, okay, so if you compute your ICR at level M, given your actual type that you're given, So you're given a type Si, and you want to compute your ICR at level n, it has to be the best response to your belief over K and ICR n-1 of the other players. Okay, and this is exactly what the obedience constraints say, right? So the comment I was giving about this is that there is, well, okay, that's a revelation principle. Okay, the revelation principle is that a common prior and its associated distribution on the strategic type space induce the same rationalizable distributions. Of course, they are obtained by the limit. So this is a revelation principle, but in a way which is very parallel to the revelation principle in mechanism design. You say, okay, you have a space on which you can work. That's the same space. Now you don't have to work on every potential mechanism in anything. And you have, you know, this identity map chosen by the players at equilibrium. Here, they don't choose, but what you have is that you give them their type already. So instead of giving the actions that they have to choose, you give them their whole sequences of ICR, okay? And you see that you come from starting with any potential distribution of types and projecting to the space through ICR to working on this space, but now you have constraints on what you can do on this space. And these constraints are given by the obedience constraints, okay? In mechanism design, they would be given by incentive constraints. Okay, so so what we did is the first step. Okay, we reduce the problem to a canonical type space, and we know what are the solutions on this canonical type space, and they are given by the obedience constraint. Now we want to use the recursive structure, and this is going to be through the notion of automaton. So let me show you on the game, because otherwise it will look very abstract and maybe more complicated than necessary. Okay, take this game. This is essentially the email game. Okay, so this is the game which on the email game is played with high probability. That's a coordination game where AA is an equilibrium, BB is an equilibrium. Okay, you can talk about risk dominance and Pareto dominance, but this is not really our purpose. What matters is that we kind of perturb these games. So we think of the game on the right as having low probability. And on the game on the right, you see that B is dominant for each of the players. Okay, so if a player believes that the game on the right is played with high enough probability, this player will play B. And if a player here believes that the game is the game on the left with high enough probability, but believe that the other player is playing B, then this player will play B, okay? And that's a whole system of contagion. So we want to represent, basically, the term is orbits, okay, or chains of ICR and ICR pairs for the players for this game. So you start first at AB, okay? Each player has a set AB, and they can stay at AB if they believe that the set is the one on the right is not too high, then they stay on AB. And they can stay at AB for a certain number of periods until they could move to either BB, because they suddenly believe that the other player may have switched to B, okay, even though the other player didn't switch to B. There may be, or only one of the players may move to only rational actions B, and the first player stays at AB. And once you're there, you can stay for a certain number of periods, or I say periods, that's not right, a certain number of levels of ICR. Okay, I'm kind of thinking with time, but it helps the intuition, but that's not proper. That's really levels of ICR, and then eventually you could move to BB. Okay, so that's kind of the chains that you can obtain. I'm not saying that all of these chains could be obtained with what probability so far. I mean, I think they could all be obtained, but I'm not talking about the probabilities of obtaining them. Okay, so this is very nice here, and really, basically, I mean, it looks like the automaton is something, I mean, perhaps too complex for what we need. Basically, we say, okay, any decreasing sequence is fine. Okay, you can obtain any decreasing sequence, and you don't have to worry more about that. Okay, so let's look at this game. This game is a coordination, anti-coordination game. Here, this is a coordination game, so we think of it like the game on the left. Okay, this game is a little bit like a perturbation, like in the email game, except for one thing. It is that here you see that A is a dominant action for player 1 and B is a dominant action for player 2. Okay, so the perturbation is if one player believes that this is a game with high enough probability and this player is player 1, then this player will play B. But if this player is player
2, this player will play A. Okay, so there is an asymmetry between the players. So if you look at first order rationalizable types or first order ICR, it could be AB, let's say for player 1, but if player 1 believes that this is the game with high enough probability, player 1 may switch to only B. And for player 2, it could be AB or only A. Okay, now let's look at second order ICR. So let's say if player 1 started with AB, then if player 1 believes that player 2 may have switched with high enough probability, player 1 believes that player 2 may have switched to B, and therefore player 1 believes that player 2 may have switched to A, and therefore player 1 may switch himself or herself to A. Okay, so you see that this kind of goes the other way around, right? So in the first round, player 1 may switch to B, and in the second round, player 1 may switch to A. And for player 2, that's the other way around. Player 2 may switch to A in the first round or to B in the second round. Okay. And if you go up like this, you obtain kind of a clock system, you know, odd even system. Okay. So the way to describe the automaton or the ICR sequences in this would be you start with AB. If you start with AB, you could move to B and A, both players switch. That's fine. You could move to AB and A, okay, in the first period, or to B and AB, okay? And in the second period, you could move to AB and B or to A and AB. And in the third period, if you didn't move at all, of course, you could move to like the first and so on, okay? So the automaton is like this here, where you have here a cycle, and here you have branching out from the cycle. Okay, and this is what is important to capture, is that we do have these cycles in some places, and this is what makes the analysis a little bit more complex than what it may look at first. Okay, and this is what we want to capture. And of course, once you have exited to ABA, you may stay in ABA forever, or or for a number of periods. Then you may go to AA, and all these sets there are absorbing. I see that there are specialists of stochastic games. Okay, so the definition of an orbit is I think natural. I don't have so much time, so I want to go a little bit quickly now. The idea is, we define ICR as a set of possible sequences in general, arising from any beliefs. Now we want to fix the beliefs at the zeroth order. So we want to fix all the beliefs of each player I over K and B minus I. Okay, we start with fixed beliefs because we think that there was kind of already a certain past, and the beliefs of each of the players are a sufficient statistic for everything that we need at this moment. Okay, so we have this PI here. So, well, we could want to index the tree or the automaton by the PI, but this is too big of an item. What we do care about is just what we call the orbits. The orbit of P is basically the set of sequences that may arise from any common priors if today's beliefs are given by P. Okay, today's profile of beliefs given by P. And we have a proposition, which is an important one here, that says that the set of orbits you can generate this way is finite. Okay, it's finite. So this is the basically similar, because maybe not exactly the same details of the model as Rafael presented, but basically the same idea that you have a finite set of orbits. So therefore, you have something which is only finitely generated. Okay, so what you care about today, you have certain profile of beliefs. You care about what is the set of possible future histories you will that can arise on STS starting from today. Okay, so from that we define the strategic automaton. To define the strategic automaton, we need to define an initial state. Remember, a state, well, a state for us is going to be a set of an orbit set. Okay, so a sequence, a family of sequences of ICR. Okay, so in the beginning, all the ICR sequences are possible. Then you have a set omega, which is a set of all the possible orbit sets together with the initial set. You have action sets. Okay, an automaton typically has a set of states, actions, transitions. Okay, so the action sets, well, whenever you're in a certain state, what's important here is that you see this tells you that all the beliefs of all the player I of each of the player are fixed and are equal to what comes just before. So this means that if you take any orbit, the first element in this orbit set will be the same for the first coordinate will be the same for all elements in this orbit set. And this first element is the best response to their belief. And therefore this pins down any orbit set pins down uniquely an action set for each of the players. Okay, and finally, you have a successor relation, which is defined in the same way as Rafael did, meaning that, if you have a set of sequences, then you may have one just coming before, and this is a successor relation that is natural, and this defines the strategic automaton set of states, action, and successor relation. Okay, so just think of this item as what you saw on the different pictures. Okay, now what I'm trying to move towards to is the idea that instead of working on the STS is nice, but the STS doesn't give you the recursive structure properly, okay? To have the proper recursive structure, you may need to have a little bit more information than the STS. You may have two states with the same action sets for the players, but they are different, just like in this coordination and anti-coordination example, okay? So what I'm saying here is that if you have any belief on the STS, any common prior on the STS, this will define a sequence on the automaton. Okay, this will define a process on the automaton. So now you can look at all your common priors are processes on the automaton. And what you are asking yourself is, what are the processes on the automaton that can be generated through common priors? Okay, the same way we had a first revelation principle, we ask, what are the beliefs on the STS that can be generated by common priors? Now you ask the same question for the automaton. And the answer is very similar in the sense that there are three properties equivalent. One is that, okay, some process or some probability distribution on the automaton are the image of a common prior, if and only if it's the image of itself. So what do we mean by the image of itself? We mean that each player knows her own sequence of coordinates of ICR that are visited by the automaton. And the third is that it has to satisfy something, which is that it starts at the initial state with probability 1. And the next constraint that replaces the obedience constraint is what we call the orbit constraint here, which is just this. It just says that the state M, okay, can be computed through the beliefs that each player I has given her own type Si on what the state S minus 1 is for all the other players, and K, okay? And it's just the orbit for that, right? So if this is the case, okay, now we have a certain family which is characterized basically by all these orbit constraints together with this initial constraint, which is not much. And if a certain probability distribution on the automaton sequences verify all that, we say it's an automaton common prior. So we may think like, okay, we're almost done. Well, except that there are still many processes on the automaton, okay? And we want to reduce our search to a class which is much smaller on the automaton, and these are what we call Markov priors. So a Markov prior is basically a prior that gives you a Markov chain on the automaton. Okay, the probability of next state according to all the paths on the state of nature depends only on the current state omega m and the state of nature. Okay, and there is a result here. Finally, I mean, not just a representation result in terms of you can use this space or you can use that space if you follow this and that rules that was useful. But here we can really do a reduction of the set of priors that we can use. We say, if you care about most specified rationalizable distributions, and these are the ones that give you the most information about what players choose, then you can focus only on Markov automaton common priors. Okay, so that's a good thing. You can just look at Markov chains on the automaton. Now, if you look at the Markov chain on the automaton, you have, of course, a finite number of parameters, but you want to check that the Markov chain on the automaton satisfies all the orbit constraints, right? You say, okay, let me look at all the Markov chains on the automaton. I look at only the ones that satisfy the orbit constraints, and they give me everything that I want. You see, the problem we have here is that the family of Si for player I is infinite, okay? And therefore, you have an infinite number of orbit constraints for each of the player I, okay? Because you have a constraint for each type Si of player I and each M, but that's an infinite number of constraints. So we want to reduce further, and we want to reduce to a finite number of constraints, and not just to Markov chains with an infinite number of constraints, okay? So here comes a final definition, which is belief stationarity, So we say we have a process on the automaton, and we look at the mth information set of type Si. Okay, what is it? Well, this is the set of n-1 types, n-1 states, sorry, according to that have positive probability according to type Si. Okay, so where could that have been just before? Where was everyone in terms of state just before? Okay, and the Markov prior is stationary if the belief on where we're coming from, okay, which is what we care about in this orbit constraint, only depends on the information set. Okay, only depends on the information set, doesn't depend on the type, it doesn't depend on M, on the level. As long as I know I'm in some information set, I have only one belief in this information set, and I don't have to care about other things. So you see that if I reduce to things that are belief stationary, I'm going to have only a finite number of constraints because I can have only a finite number of beliefs. Okay, so that's a good thing. So let's see how we can reduce to belief stationary processes and what they look like, and also what do the information sets look like. So this is a Markov prior for the email game. By the way, I kicked out transitions to BB just to simplify the picture a little bit. Okay, so we don't have them, but you could include them if you wanted something more complete. So we start with AB, we move to ABB or BAB, or we stay, and then we may stay on, or we move again. Okay, so let's look at the type of player one, which is, well, this type of player one is ABAB for a number of rounds of ICR, and then switch to A. Okay, so the first time, or according to when I start at level 0, let's say, I know that the other player is at level 0, right? So my information set is only this, okay? I know that I'm here, okay. Next, let's say I didn't switch, but what do I know? I don't know if the other player switched or not, right? So I may be here, or I may be there. So my information set is this and that. Okay, and what is my relative probability? Well, I'm going to stay in this as long as I don't switch. Okay, so if I don't switch, I'm still in this set, right? But what is the relative probability of those two automaton states, ABB and ABAB? You see that further we progress, the higher the probability of this state. Okay, the probability is going to depend on how long we stay. Okay, that's why the number of constraints is going to be infinite. We're going to, that's going to be a little bit, it's not a finite number of constraints here. Okay, and then let's say I just moved to B. Okay, so either I was the first to move to B, and then we are here. Okay, or I was second to move to B, and we are there. And then, well, I moved to B, and I moved to B like at least 2 periods ago, right? Or something like this. So maybe we are here actually, because I moved first, the other moved second, or the other moved first, the other moved first and I moved second, okay? And then we are there. Or I moved first and the other never moved, and we are there, okay? So this is my information set. So we have 1, 2, 3, 4 possible information sets here. Now, what we say and is that if you care about more specified distributions, we can simplify this, okay? Because basically, if you stay here, okay, eventually, if this probability P35 is positive, you're going to go to BB, okay? Eventually, you're going to go to BB. So we can kill this transition that stay here, okay? And the point is that we can kill them in a way that satisfies obedience constraints or orbit constraints, okay? That needs to be checked. And this comes from the convexity of best response correspondence. So that's not something too big. It comes from Bayes' rule and convexity of best response correspondence. So what do we say is that, well, we can simplify this chain instead of having a transition back here and then there. Whenever we here, we move there directly. And same thing, whenever we here, we move there directly. Okay? And when you are here, we may stay here. Okay? But that's a simplification. So now what are my information sets? One is here. Okay, well, if I stay, if this is my information set, I know the other is here. So I have only one possible belief, of course. Now, if I didn't move, okay, I see that the probability of this versus that, I mean, this yellow set here, okay, is just given by the transition probability P14 with respect to 1 minus P14 or something like this. Okay. Now this is going to be just dependent on the fact that I consider those two as possible. right? So this is going to be belief stationary now, right? And here, when I arrive to this set, well, what matters is the relative probability I exited here and I exited there. And this is something like the ratio of P13 and P14 or something like this, okay? So I don't have to worry about these things. I have something which is belief stationary. Okay, so the whole point is this result, of course, that every most specified reasonable distribution is induced by a belief stationary automaton common prior, okay? Once we have things that are belief stationary, we have things that are finitely dimensional because they are Markov, okay? And they are also given by a finite number of conditions. And those finite number of conditions, they are algebraic conditions. They express basically ratios of, you know, being in certain state where, as opposed to another state in a Markov chain where the belief doesn't depend on the, you know, on a lot of things. It just depends on the information set, okay? So it will be polynomial, if you want, in the different transition probabilities, okay? And therefore, this is algebraic, all right? So what have we learned about most specified rationalizable distributions? We have learned that they are characterized through a finite number of algebraic conditions, okay? So they form an algebraic set. And if you care about information design, okay, now you want to kind of reverse engineer the whole problem. It's not as simple, of course, as in correlated equilibrium. That's very linear. That's linear, and that's you know, very nice, elegant, and simple. Okay, here it's more complex because it's algebraic. So, but if you have your distribution that you know is rationalizable, you will have to look at it as the limit distribution for some automaton. Then you construct the automaton. Okay, and once you construct the automaton, you can move the automaton to a certain distribution over the STS, basically, and say, okay, now this is the distribution of types you give to the players. And if you want, this is, I hope, I mean, I was able to convey this, because I didn't mention it, you know, very specifically. If you look at the email game, okay, the email game has very recursive structure, okay, very clearly. I mean, the information has a very recursive structure. The information in the email game, remember, I send you an email, it may get lost or not. If you get it, you send it back, it may get lost or not. And it's always the same probability of getting lost and not getting lost, okay? Why don't people look at, you know, weird probability? Well, basically because it's not so useful, okay? You just have to look at the same probability all the time because you have something which is, you know, Markovian, which is recursive, okay? And except that the email game, you see, has a rather simple automaton, okay, in terms of transitions, right? If you have a more, I mean, first it has 2 actions per player, so we know more or less what to say about all these games. But if you look at a game, even like this, with 2 actions per player, but that does have certain cycles, well, you have to be more careful in the way that you do the transitions, okay? You have to be, you really have to look more carefully at the automaton in order to generate the information. Okay, so that's why we think that the automaton is really capturing again the recursive structure of ICR. Okay, the strategic type space is nice for kind of quote unquote Mertens-Zamir purposes, if you want, but this is really capturing the recursive structure. So if you want to apply the recursion, we think that this is the right tool to work with. Okay, sorry, I went over time. Sorry for the complications.
Yes. Thank you, Olivier.
Thank you.
And now people can ask questions. Feel free to unmute yourselves, people. Well, if there are no questions, everything is clear, then we thank you again.
Okay, thank you so much again. It's great to see many faces. I hope to see you in person soon. Yes.
Okay.